Welcome to this week's first lecture. In the last week we have started with the topic of Hermitian matrices, and today we are going to continue with the properties of Hermitian matrices. So let us remember what we have done so far. So we call a matrix Hermitian if it is Hermitian is equal to itself. So we have a Hermitian matrix satisfying this property. And then we have seen some properties of Hermitian matrices. So we have seen that such an inner product, this is also X Hermitian AX, is always real. Real for all X. Okay? This was the first property that we have seen for the Hermitian matrices. The second property that we have seen is about eigenvalues. So lambda i's are all real. Okay? So this is true for all I. So we have seen that all of the eigenvalues of A should be real. Okay? In the general case, a matrix, even a real valued matrix can have complex eigenvalues. In this case, we don't. So even there are complex elements of the Hermitian matrices, there can be, then we won't have any complex eigenvalues. So the second property the third property is about the eigenvectors. So if lambda I is not equal to lambda j, then the eigenvectors corresponding to these eigenvalues, EI and EJ, are orthogonal. So we have seen that in the course for a general matrix, a non-Hermitian one, when we have distinct eigenvalues, we would have linearly independent eigenvectors. Okay, so this is a stronger property for a Hermitian matrix. When we have distinct eigenvalues, eigenvectors belonging to those distinct eigenvalues should be orthogonal. Okay, and then we have seen a property related to the minimal polynomial. Suppose that this is the characteristic polynomial of a Hermitian matrix, S minus lambda 2 R2 going until S minus lambda k rk. So we have k distinct eigenvalues like this. And the minimal polynomial for a Hermitian matrix is always going to turn out to be in the following form. S minus lambda k. So this means that all of the powers, all of the multiplicities in the minimal polynomial should be 1. Okay? So that means that, in other words, mi is equal to 1 for all I. All right? And this told me something about the Jordan canonical form of the Hermitian matrix. So let us remember that at the minimal polynomial power here, at the minimal polynomial multiplicity, we reach the largest null space. Okay? Null space of A minus lambda I identity for a Hermitian matrix would be equal to A minus lambda I identity to square. Okay? So we would have this equality. Therefore, this is the largest null space. The largest null space is reached at the power 1 because mi is 1, and the dimension of this one would be R1. Okay? Sorry, not R1, Ri, of course. For each eigenvalue, the dimension of the largest space would be the characteristic polynomial power. All right? So now this gave us the general decomposition of Cn for a Hermitian matrix. And in that case, I would have, since the largest null spaces are the eigenspaces, I would have this type of decomposition going until null space of A minus lambda k identity. And we have, so the dimensions of these spaces would be R1, R2 going until Rk, just as in the general case, but the powers of the decomposition here would be all 1, because the minimal polynomial multiplicities would be just 1. Okay, so here the interesting thing about this decomposition is that this is, in addition to a direct sum being a direct sum decomposition, this is also an orthogonal direct sum decomposition, and that is because these are my eigenspaces. So we are decomposing Cn into a direct sum decomposition of eigenspaces, and in each of these spaces any non-zero vectors would be my eigenvectors, because eigenvectors are non-zero vectors living inside the eigenspace. So here I can say that the vectors here would be orthogonal to the vectors in the second null space. Similarly, in the other null spaces, in the other eigenspaces, because the vectors here would be eigenvectors, and except for the zero vector, but zero vector is orthogonal to all vectors. So the eigenvectors here would be orthogonal to eigenvectors here, or the eigenvectors here. Okay, so that means that here, so we have already said that distinct eigenvectors corresponding to distinct eigenvalues should be orthogonal. That means that these spaces are orthogonal to each other. So we have an orthogonal direct sum decomposition of Cn into eigenspaces for a Hermitian matrix. As you know, if Mi is not equal to 1 for all I, we wouldn't have such a decomposition for a general matrix. In the general case, we won't have the orthogonality conditions, and we would have powers here, minimal polynomial powers on top of these matrices. Okay? So now we can actually look at the Jordan canonical form of this matrix, or an Hermitian matrix. And when I look at these null spaces, the dimension of this largest null space is Ri. That means that the dimension of the null space of A minus lambda I identity square would be also Ri. Okay? So what does that mean? So what is the number of Jordan blocks for the eigenvalue lambda I? Number of Jordan blocks for lambda I would be this dimension of the eigenspace. So this is equal to Ri. And what is the number of Jordan blocks whose size is larger than or equal to 2? In that case, that would be this difference, dimension difference here. So number of Jordan blocks with size larger than or equal to 2 for lambda I would be that difference here, but this should be 0, because the eigenspace is the largest null space. So that means that there are no Jordan blocks for lambda I whose size is equal to 2 or whose size is strictly larger than 2. That means that all Jordan blocks should have size 1. Okay? But this is also coming from the fact that Mi is equal to 1. Remember, Mi would be the size of the largest Jordan block for the eigenvalue lambda I. So the size of the largest Jordan block we have would have size 1. That means that all of the blocks would have size 1. So I have, in this case, combining these two facts, we have for lambda I, we have Ri Jordan blocks with size equal to 1 for lambda I. Okay? For each eigenvalue, we have as many Jordan blocks as the characteristic polynomial powers, and size of each of these blocks would be 1. So if I try to obtain the Jordan canonical form for this matrix, I have lambda 1s as many times as the characteristic polynomial power here, 1 by 1 blocks. So this is R1 times. So each of these blocks would have size 1 by 1. Therefore off diagonal elements would be 0. And then lambda 2. So I have 1 by 1 blocks going until lambda 2, until I have here R2 times lambda 2. So again, I have 1 by 1 blocks, and everywhere else in this block would be 0. And finally, I have lambda k and 1 by 1 blocks, lambda k, and going until the last element where I have lambda k. And here I would have this many blocks, Rk block, 1 by 1 Jordan blocks. So again, this is off diagonal elements would be equal to 0. So the Jordan canonical form would be surely diagonal in this case, because all of the Jordan blocks have size 1 by 1. And it would look like this. So I would have here as you see here, this is nothing but lambda 1 times an R1 by R1 identity matrix. Lambda 1 times identity R1 by R1, lambda 2 times identity R2 by R2, going until lambda k times identity RK by RK. Okay, so and I would have zeros everywhere else. So the Jordan canonical form of a Hermitian matrix is always diagonalizable. Is always diagonal. So a Hermitian matrix is always diagonalizable. Okay. So that is one of the properties. So J is diagonal, and A is diagonalizable. These are the general facts. And now we're going to see, so this was a review of what we have seen so far. So now we can continue with the last property that we are going to see. Actually, we are going to see some more advanced properties, but this is going to be one of the basic properties here. The next thing that we are going to see. So let us write the theorem for this. Let A be an n by n Hermitian matrix. Then there exists a unitary matrix P. A unitary matrix is a matrix which would satisfy the following property. P inverse is equal to P Hermitian. So a unitary matrix is a matrix whose Hermitian is its inverse. All right? Such that, ST means such that, Jordan canonical form, that diagonal Jordan canonical form is equal to P Hermitian AP. Okay? I will try to give the idea of this proof because it is very important for Hermitian matrices. And here we are talking about this property is talking about the P matrix, the basis change matrix. And we are saying that in the general case that P matrix has to be invertible. The only thing that we know about the P matrix in the general case is that it needs to be invertible. So that means that its columns are linearly independent or its rows are linearly independent. Here we are saying something else. We are saying that this P matrix satisfies this interesting property of being unitary. Unitary matrices are some magical matrices which has orthonormal columns. So P matrix is not only composed of linearly independent columns as in the general case for a Hermitian matrix, but P matrix can have orthonormal columns. So each column is orthogonal to all of the other columns, and the columns can be normalized. So in general, for a general A matrix, you can always normalize the columns of the P matrix. So normality is not really a problem, but the orthogonality will not be satisfied for a general A matrix. For the Hermitian case, the P matrix, we can find the P matrix which is composed of orthonormal columns, both orthogonal and normal. So let us first try to understand why unitary means orthonormal columns. So here let us say that P is unitary. Okay? Then we know that P inverse is P Hermitian. Okay? What does that mean? When I multiply P Hermitian with P itself, or when I multiply P with P Hermitian, then I'm always going to get the identity matrix. Okay? That is what being unitary means. In general, the only matrix that you can have this type of property is P inverse. But here we see that P Hermitian satisfies this property. That means that P inverse is equal to P Hermitian. okay, for a unitary matrix. Let us now try to understand what this means. So I'm going to be looking at the expression P Hermitian P is equal to identity. All right. So now I'm going to expand P in terms of its columns. Let us say that P has the following columns: P1, P2, going until Pn. P is an n by n matrix, just like A. Okay? So all of these columns are in Cn. All right? So now, this is my P. Then what happens to P Hermitian? P Hermitian is the Hermitian of this matrix. That means that the columns of this P would be, I will be taking the Hermitian of the columns, and the P Hermitian will have the rows P1 Hermitian, P2 Hermitian, going until Pn Hermitian. Okay? So I would have P Hermitian matrix in this form. If P is composed of these columns, then P Hermitian would be composed of Hermitian of the columns of P as it is rows. All right? Now let us try to multiply P Hermitian with P. P Hermitian times P is equal to, I will first write P Hermitian here, P1 Hermitian, P2 Hermitian, going until Pn Hermitian, times P itself, P1, P2, going until Pn. All right? Now we can use the rules of partition matrices to write the n by n matrix. So we see that here, the first column of the multiplication would be P1 Hermitian P1, and then I would have P2 Hermitian P1, and then I can continue Pn Hermitian P1. These are now inner products, L2 inner products of P1 with itself, and the L2 inner product with P1 with P2, and then L2 inner product of P1 and Pn. This is my first column. These are scalars, and this is my first column of the multiplication. Okay? So when you multiply two matrices, then what you are doing is basically you are taking the inner products of the rows of the matrix on the left with the columns of the matrix on the right. Okay? This is the general matrix multiplication rule. And then you would have the second column, P1 Hermitian P2, and then you would have P2 Hermitian P2. These are continuing like this, and I would have Pn Hermitian P2. So these continue until the last row, and P1 Hermitian Pn, P2 Hermitian Pn, this is the last column, and Pn Hermitian Pn. Okay? So this is the multiplication of P Hermitian with P itself. Okay? And I know that for a unitary matrix, this should be identity matrix. Okay? But before that, I will write these terms here, each of these scalars as inner product. So P1, L2 inner product. So this is P1 inner product with itself, and this is P1 inner product with P2, and these are continuing until P1 inner product with Pn. Okay? Remember our inner product definition, xy is equal to y Hermitian x. This is my inner product definition. And as a result, this matrix is nothing but the inner product of P1 with P2. Okay? So then I can write here the other terms. So P2 with P1, and I can write P2 with P2. So I can continue in this manner, P2 and Pn. Okay? And I can go into the last column here, Pn inner product with P1, Pn inner product with P2, going until Pn inner product with Pn. Okay? And I know that for a unitary matrix, this multiplication should be identity matrix. That means that this is identity matrix. So I have 1, zeros everywhere else, 0, 1, zeros everywhere else, and at the last row, zeros everywhere until the last element. So I have an identity matrix. So this is identity. So what does this mean for these elements? So let me try to write the first column, second row. So if I write the P Hermitian P, ijth element of the P Hermitian P, its ith column, its ith row, jth column element. What is going to be? So for example, this one is the first row, second column. Okay, this one is the second row, second column. This one is the second row and nth column. Okay, so we see that this is actually equal to, according to this relationship, would be, I would have the inner product of Pj with Pi. Okay, ijth element of the matrix P Hermitian P is this inner product. Okay. And here, what are the ijth element of the identity matrix? I know that this is nothing but delta ij. So when I is equal to j, the result is 1. When I is not equal to j, the result is 0. Okay? So we see the following fact about the columns of the P of the matrix P. So the inner product of the columns would be equal to 1 when I have I equals to j, and the inner products would be equal to 0 when I is not equal to j. So the inner product of distinct columns, inner product of the different columns would be equal to 0. So each column of the matrix P would be orthogonal to the other ones. All right? And the norm of each column would be 1. So let me try to write this in a clearer way. So I see here that this Pj, Pi is equal to 1 when I is equal to j, and if I have I is not equal to j, then otherwise, instead of otherwise, I can write I is not equal to j, and it's going to be 0. Okay? So this means that the inner product of Pi with Pi, this is going to be 1. But this is nothing but Pi norm square, L2 norm square is 1. This means that Pi norm is equal to 1. Okay? So we have just this normalization property. Each column of the unitary matrix P would be normalized. It would have norm 1. And furthermore, it is going to be orthogonal to all of the other columns. Right? What about the rows of a unitary matrix? If the columns of the matrix is actually orthogonal to each other when it is unitary, what about its rows? The magical property of unitariness would also necessitate the rows to be orthonormal to each other. Okay? So here we use this property, P Hermitian P is equal to identity. If you use instead the other property, P times P Hermitian is equal to identity, then you can show that the rows of the matrix P would also be orthonormal to all of the other rows. So rows would be normalized, and it would be orthogonal to all of the other rows. Okay? And this is coming from the second equality. So for the columns we used P Hermitian P is equal to identity. If I use the other property here, P times P Hermitian is equal to identity, I could have shown that the rows of the unitary matrix would also be an orthonormal set. Okay? So here, the magical property of a unitary matrix is that if you fill a matrix with orthonormal columns, if you find a set of orthonormal vectors and set of orthonormal vectors, and if you fill them into the columns of a P matrix, then that matrix have to be a unitary matrix. So then the rows of the matrix would also turn out to be orthonormal to each other. That is the magical property that I'm talking about. If you make the columns of a matrix orthonormal, then its rows also would become orthonormal in a magical way. So this is the property of a unitary matrix. So it is columns are orthonormal. Now, what about the theorem here? The theorem is suggesting that you can always find a basis change matrix P which is unitary that would satisfy this equation J is equal to P Hermitian AP. In general, what do we know? In general, we know that we can find a P matrix with linearly independent columns which would satisfy this equation. Okay? In general, we can always find P with linearly independent columns. What does linearly independent column means? In general, we can find always an invertible matrix P. So P inverse is always defined. So for a general matrix, we can always find an invertible matrix P which would satisfy this equation. We have seen this. And now the theorem is claiming that we can find a unitary matrix P. In addition to this general property, we can find P which satisfies P inverse is equal to P Hermitian. Okay? But what does that mean if I combine these two facts? It means that instead of P inverse, I can write P Hermitian if P is unitary. And that is going to give me P Hermitian AP. Okay? So the theorem is actually using this general property that we know. We can always find a P with linearly independent columns, an invertible P. And the theorem says that if for a Hermitian matrix, we can always find a unitary P matrix. And if I combine these two facts, I would end up with this equation here. Okay? So now I'm going to give you the idea of the proof of this theorem. I'm not going to show you the general proof because I'm going to be assuming a special case. As soon as I start assuming a special case, the things that I write would lose the property of being a valid proof. Okay? So you need to generalize the idea that I give for a general A matrix, and then you can come up with an actual proof of the same theorem. So here, let us write the idea of the proof. So here, I am assuming the following fact. Let us say that A is in C5 by 5. As soon as I make this assumption, the things that I have written lost the property of being a proof. Because in general, a proof of this theorem should consider an arbitrary A matrix, an n by n matrix. As soon as I have written this, that nothing I can write further would make these lines here a valid proof for this theorem. So let us say that d of s is the following polynomial. S minus lambda 1 to the 2 and S minus lambda 2 to the 3. Okay? And then I would have, let us say, the minimal polynomial. So I'm assuming, of course, A is Hermitian. Okay? And then what is going to be the minimal polynomial? I have this characteristic polynomial, and the minimal polynomial should be just this one, S minus lambda 1 and S minus lambda 2. Because in this case, the minimal polynomial should have all the powers equal to 1, because A is Hermitian. All right? So now I'm actually going to be finding a P matrix for such a special matrix. Okay? And then, after finding a P matrix, I will try to show you that the P matrix that I have found can be converted into a unitary matrix, which would satisfy this equation. Okay? I will first find an arbitrary P matrix with linearly independent columns, but the columns would not have to be orthogonal to each other. So in that case, the P matrix that I find initially would not be a unitary matrix. But then I will show you how to modify that P matrix to obtain a unitary P matrix. Okay? So now here, let me start with the first eigenvalue. I know that null space of A minus lambda 1 identity is the largest null space for the first eigenvalue. And I know that its dimension is going to be equal to 2. All right? So then I'm going to find a basis set for this null space, an arbitrary basis set. Okay? So you see that there is only one concentric null space here. In this case, therefore, my chains would have all sizes 1. Okay? So remember how many Jordan blocks we had and what would be their sizes. In this case, the size of the Jordan blocks would be all 1 Hermitian matrix, and I would have 2 Jordan blocks. Okay? Remember, for a Hermitian matrix, for each eigenvalue lambda I would have Ri Jordan blocks with size equal to 1. So that means that I have, in this case, 2 Jordan blocks with size 1. Then what about our chains? I know that the number of Jordan blocks would be equal to the number of chains, and the sizes of the Jordan blocks would be equal to the sizes of the chains. So in this case, I am expecting 2 chains with sizes 1, all equal to 1. Okay? So here I find my first chain, x11. Okay? It is a non-zero vector here, so that is going to form my first chain, okay, x11. And then this single vector would not constitute a basis vector for this null space. So it is I need to have 2 vectors, 2 linearly independent vectors for the null space. That means that I need to find one more vector here, x12, which is going to be constituting my second chain. So I have 2 chains with size 1. Then I know that I need to choose these vectors to be linearly independent. So then this is going to complete the chains for the first eigenvalue. Okay? So what can I say about these vectors? So this space is an eigenspace, and these vectors are non-zero vectors inside this eigenspace. That means that both of these 2 vectors would be eigenvectors, and they are linearly independent. All right? So here I need to, of course, choose x11 and x12 should be non-zero. Actually, if I write linearly independent, that would be sufficient, because any set that is containing a 0 vector would not be linearly independent. x11 and x12 should be linearly independent, okay? And then I would complete the basis set for this overall null space by using 2 chains with sizes 1, okay? Now I'm going to, and these 2 vectors would be eigenvectors, and they would be linearly independent because of my selection here. And then I would have 2 linearly independent eigenvectors for the eigenvalue lambda 1. So x11 and x12 are eigenvectors for lambda 1. Okay? And then I go into the second eigenvalue. So null space of A minus lambda 2 identity. This is the largest null space again. And I see that in this case the dimension of this space is 3. I'm going to do the same thing here. All right? So I will do the same thing, and I will find a non-zero vector here, x21 in this case. So this is going to constitute my first chain. And then this is not going to be sufficient for being a basis set for the 3-dimensional eigenspace. So I will find linearly independent another eigenvector, x22. This is going to constitute my second chain. This is x21. And finally, these 2 chains would not constitute a basis vector for the null space, which is 3-dimensional. That means that I need to find a third chain here, which is going to be x23. All right? Now I can find here x23. So here, what are the conditions in this case? x21, x22, and x23 should be linearly independent. And I know that these vectors are eigenvectors. x21, x22, and x23 are eigenvectors. So now this completes my chain of vectors. So for each eigenvalue, I have found Ri chains with sizes all equal to 1. Okay? And then I would fill in my P matrix. P matrix would be formed by these chains x11, x12, x21, x22, and x23. A 5 by 5 P matrix. Now I can ask you the question, is this P matrix a unitary matrix? What I know here is that these two columns are linearly independent with each other. These three columns are linearly independent with each other. What else do I know? I know that for a Hermitian matrix, eigenvectors belonging to distinct eigenvalues are orthogonal to each other. So this means that the vectors in this null space would always be orthogonal to the vectors in the other null space, and vice versa. Okay? So because of the fact that eigenvectors belonging to distinct eigenvalues are always orthogonal to each other for a Hermitian matrix, these two vectors would be orthogonal to all of these three vectors here, or these three vectors would be orthogonal to these two vectors. So I know that this x21 is orthogonal to x11 and x12. x22 is orthogonal to these two vectors. x23 is orthogonal to these two vectors. Okay? So I know that these three columns are orthogonal to these two columns, and these two columns are orthogonal to these three columns. But what about the orthogonality of the other ones? So these two vectors, do I know that they are orthogonal to each other? These two vectors, they really do not have to be. So the only condition when I am finding these two vectors are that they should be linearly independent. I really did not enforce any orthogonality here. So these two columns, they do not have to be orthogonal to each other. Similarly, these three columns, they do not have to be orthogonal to each other. As a result, this P matrix really does not have to be linearly, does not have to be a unitary matrix. Okay? But can I obtain some equivalent vectors to these x11 and x12 and these three vectors here, which would make all of the columns of P orthogonal to each other? The answer is going to be yes here. Okay? So suppose that I start with these two vectors, x11 and x12. Suppose that I want to find another base. These two columns would form a basis for x11 and x12, form a basis for this eigenspace. Okay? Can I find another set E11, E12, such that the span of this set of vectors would be the same as the span of these two vectors, but I want these two vectors to be orthonormal. I want these two vectors to be orthogonal to each other, and I want them to have unity norm. Okay? Starting with a linearly independent set of vectors, can I find a new set of vectors with the same number of vectors here, such that the new set, span of the new set is equal to the span of the original set, and the new vectors that I obtain are orthonormal? So you have already seen such an algorithm in this course to be able to achieve this task. And this is called the Gram-Schmidt orthonormalization. Orthonormalization. So start with arbitrary two linearly independent vectors here, which is forming a basis for this null space, and then apply Gram-Schmidt orthonormalization to them, and then you would obtain some orthonormal set of vectors which are still inside this null space. So these are again eigenvectors belonging to the eigenvalue lambda 1 because the span of these two sets are the same. Span is this null space, and these two vectors would be orthonormal to each other. Okay? So you see that I can replace this basis of the first null space with this basis, with this orthonormal basis. Okay? And then I can do the same thing for the second set, x21, x22, and x23. Apply Gram-Schmidt orthonormalization to this. I am not only applying orthogonalization here because I want these vectors to have unit norm at the end. So this is orthonormalization, and this is going to give me E21, E22, and E23. These would span the same null space. They would be still eigenvectors, and furthermore, they would be orthonormal. And then, instead of forming my P matrix like this, because it is not unitary in general, I would fill my P matrix out of these new basis sets. E11, E12, E21, E22, E23. Okay? And then I know that these three vectors are still orthogonal to these two vectors because they are in null spaces for distinct eigenvalues, eigenspaces for distinct eigenvalues. They would still be orthogonal to each other, and furthermore, these two vectors are orthonormal among themselves, and these three vectors would be orthonormal as well. So we actually satisfy the property of orthonormality by all of the columns of such a P matrix. Okay? Then when I look at P Hermitian P, I would have the following matrix: E11 Hermitian, E12 Hermitian, this is P Hermitian, and E21 Hermitian, E22 Hermitian, and E23 Hermitian. Okay, this is P Hermitian, and P itself is E11, E12, E21, E22, E23. And then we know that at the end, this matrix multiplication is going to give us the inner products of these columns with their selves. Okay? The first row, first column element would be the inner product of this vector with this one. So this is going to be inner product of E11 with itself. So that is norm of E11 squared, but norm of E11 is 1 because it is a vector that I have obtained using Gram-Schmidt orthonormalization. Okay? So this is going to be 1. And the second element would be the inner product of these two vectors. So because these two vectors are orthogonal to each other, such an inner product would give me 0. And furthermore, if I obtain the third row here, it is going to be the inner product of these two vectors. These are eigenvectors belonging to distinct eigenvalues. That means that this inner product would be equal to 0 as well. And similarly, the other inner products would be 0. If you fill in then this matrix, you would see that this is going to be an identity matrix with 1s on the main diagonal and 0s everywhere else. So this is identity 5 by 5. So you see that this shows that this new P that I have found is going to be a unitary matrix. Okay? So P is unitary. So you see that we can find some non-unitary matrices as well. So this theorem doesn't tell us that all P matrices you find will be unitary. It only says that you can find at least one unitary P matrix. Okay? So there can be non-unitary matrices, P matrices that you can find, of course. But here the fact that you can always convert that matrix into a unitary matrix, and that proves the theorem here. So in order to be able to obtain a general proof for this theorem, you have to start with a Hermitian matrix which is in Cn by n, and then you have to put here some arbitrary number of distinct eigenvalues and arbitrary powers here, And then the minimal polynomial should contain arbitrary number of eigenvalues. And here you should have arbitrary number of null spaces. And then you would find these chains and you would complete these ideas into obtaining a unitary P matrix at the end. Okay? So this completes giving the idea of the proof of this theorem. Okay? So now let us try to understand what this theorem or how this theorem can be used. So we have seen that Jordan canonical form can be written as P Hermitian AP, and P is composed of orthonormal columns. Okay? So let me call these columns now E1, E2, En. I know that these columns are eigenvectors, right? So here, whatever I do here, the vectors that I found will always be eigenvectors because they will be inside the null space, inside the eigenspaces. Okay? So let us say that P is composed of these eigenvectors, and I know that they are orthogonal to each other. EI is orthogonal to EJ when I is not equal to J. And I know that norm of EI square is equal to 1. Norm of EI is equal to 1. And let me write the Jordan canonical form as follows. Lambda 1, lambda 2, going until lambda n. Some of these lambdas might be the same, right? So, but I have shown here all eigenvalues with distinct characters here. So, although here some of the eigenvalues can be the same. So lambda 2 can be equal to lambda 1, for example. Okay? So let us say that this is my Jordan canonical form. The name of each eigenvalue is different, although some of them can be repeated. And I have here denoted all columns of P as the eigenvectors. Okay? Although some of those eigenvectors might belong to the same eigenvalue. So here is what I'm going to do. I'm actually going to try to write A in terms of its Jordan canonical form. Okay? So let me write A instead of J. A is equal to, I will multiply both sides of this equation with P from the left, then P times P Hermitian would be identity. So on the left I have Pj and P Hermitian here. In general we know this. A is equal to Pj P inverse. Okay? Since here P inverse is P Hermitian because we have a unitary matrix, I replace P inverse with P Hermitian. Okay? So now this is my A in the Hermitian case. And I have A is equal to, let me write P here, E1, E2 going until En. And then I will write the Jordan canonical form, lambda 1 going until lambda n, a diagonal one. And then I will write P Hermitian there. So P Hermitian is E1 Hermitian, E2 Hermitian, going until En Hermitian. Okay? Then I have such a matrix multiplication. So if I multiply this diagonal matrix with this matrix, then this diagonal matrix multiplication will multiply each row of this matrix with the corresponding eigenvalue. Multiplying a matrix with a diagonal matrix from the left will multiply each row with the corresponding diagonal element. Okay? So I have E1, E2 going until En, and this multiplication is going to be lambda 1, E1 Hermitian, lambda 2, E2 Hermitian, going until lambda n, En Hermitian. Okay? If you multiply a matrix with a diagonal matrix from the left, it is equivalent to multiplying the rows of that matrix with the corresponding diagonal elements. Instead, if you multiply a matrix with a diagonal matrix from the right, then the resulting matrix is the columns of that matrix weighted by the corresponding diagonal elements of the diagonal matrix. Okay? That is the effect of multiplying a matrix with a diagonal matrix from the left or from the right. And then if I do this multiplication here, then I'm going to take this matrix and I will multiply it with this column, with these columns. Then it's going to give me the following resulting matrix: lambda 1, E1, E1 Hermitian, plus, so this is like an inner product with permutation matrices, plus lambda 2, E2, E2 Hermitian, going until lambda n, En Hermitian. Okay? But this is nothing but the following summation: I from 1 to n, lambda I, EI Hermitian. Okay? So this shows that this theorem tells us that when we have a Hermitian matrix, that Hermitian matrix can always be written as the summation of eigenvalues times some rank 1 matrices, E1, E1 Hermitian, E2 Hermitian, times eigenvectors times eigenvectors Hermitian. So for each Hermitian matrix, we have a decomposition of it into its eigenvalues and eigenvectors in this form. This is a fact that is used in telecommunications theory or in statistical signal processing really a lot. So since the matrices that you encounter in telecommunications or statistical signal processing are almost always covariance matrices, they are always Hermitian matrices. And you can always write such a decomposition for any Hermitian matrix. So this fact is really an important fact coming from this theorem that we have seen. So now I'm going to write a theorem, but I won't be able to prove it actually. I will leave the proof as an exercise and I will upload the proof to the class. But the proof is also inside the lecture notes that we have put into the class, so you can check them separately from the notes as well. Well, let us look at a theorem. This is again a property of a Hermitian matrix, but in this case we have a more advanced property. Well, let A be an n by n Hermitian matrix with eigenvalues lambda 1, lambda 2, going until lambda k. So these are the distinct eigenvalues, okay? So here, there can be, the multiplicity of lambda 1 will be R1, multiplicity of lambda 2 will be R2, etc. But the total number of eigenvalues, of course, is n. And here I'm counting only the distinct eigenvalues. Let us say that lambda minimum is the minimum of the eigenvalues over I. And let us say that lambda max is the maximum of the eigenvalues. Here, because the Hermitian matrix eigenvalues are always real, we can talk about their minimum and the maximum. In general, for a general matrix, since the eigenvalues are complex, we cannot really talk about the minimum of the eigenvalues or the maximum of the eigenvalues because they might not be real quantities. In that case, taking minimum or maximum of complex quantities really does not make any sense. But since the matrix is Hermitian here, we know that these eigenvalues are real. Okay? So we can talk about their minimum and maximum. Then we have XAX. We know that such an inner product is always real, is always smaller than or equal to lambda max XX, and is always larger than or equal to lambda min XX. Okay? So this is the statement of the theorem, and we are said that equalities are satisfied. So this smaller than or equal to, or this smaller than or equal to, becomes an equality when x is equal to E min and x is equal to E max. Okay? So here E min and E max are the eigenvectors for lambda mean and lambda max. Okay? So we are said here that this inner product here is always between two quantities, and these two quantities are given by the minimum and the maximum eigenvalues. I can actually write this fact as follows. This inner product is nothing but x Hermitian AX. Okay? And this is nothing but lambda max times x norm square, and this is lambda mean x norm square. Okay? So I have just this fact. So here I'm not going to be able to prove this because of lack of time. Instead, I'm going to look at some useful property that we can derive from such a theorem. Okay? So here we are said that this inequality holds, and even I can satisfy the equalities if by choosing x's as the corresponding eigenvectors for lambda mean and lambda max. Okay? So now suppose that x is not equal to 0. Okay? Suppose that x is not equal to the 0 vector. In that case, this inner product is going to be non-zero, and then I can divide all sides of this inequality with x inner product with x. So that is going to give me xax is between lambda max. I have division here, xx. Okay? When x is non-zero, I can divide by the inner product of x with x, because that inner product should be always positive when x is non-zero. And this is lambda mean. And this should be true for all non-zero x's. Okay? So this theorem is actually telling us that this ratio is always between lambda mean and lambda max when x is non-zero. If x is 0, this ratio doesn't make any sense because the denominator is actually 0. Okay? So we see that for any Hermitian matrix, we have this type of property. This ratio, it's always a real quantity, and it's always between the minimum eigenvalue and the maximum eigenvalue of the matrix A. And the equalities will be satisfied if I choose x equals to E max, the equality on the right. Equality here will be satisfied when x is E max, and equality here will be satisfied when x is equal to E min. All right? So now I'm going to remind you the following matrix norm definition. So this is the maximum when x is not equal to 0, the norm of ax divided by norm of x. This is the induced norm definition for the norm of a matrix. Okay? And in this course, in the earlier parts, you have defined or find out what these norms would be when you put infinity norm here, or when you put one norm here. Okay? So here I would like to see what happens when I have L2 norms here in both of these norms. Okay? So let us try to see what this induced norm would give us. In the earlier parts of this course, we couldn't derive this because we didn't know such a property. Okay? So now let me look at the following ratio. AX2 divided by x2. Instead of looking at this ratio, I will look at the squares of this. And then if I find the result, I will take its square root to calculate the norm. So I know that maximum x is not equal to 0. This is going to be a norm square. Okay? So now let us look at this. Maximum x is not equal to 0. Ax norm square is nothing but the inner product of Ax with itself. Okay? So this is Ax norm square. And what about the denominator? It is x and x. So you see that it is getting closer to this ratio in some way when you use L2 inner product. We know that L2 inner product, we know that L2 norm square can be written as the L2 inner product of Ax with itself. And x norm square can be written the inner product of x with itself. So here is what I'm going to do. We know that in the L2 inner product, if we have an A multiplication in one of the arguments of the inner product, I can take it to the other argument. Okay? So I can actually take this A multiplication to the other argument by taking its Hermitian. Okay? So this is equal to, so x, sorry, I have forgotten the maximum. This is the maximum. X is not equal to 0. X, A Hermitian, Ax. Okay? So I have taken this one to the other side so that the resulting ratio resembles that one. And I have XX. Okay? So you see that here I have obtained the induced norm square very similar, with a very similar expression to this one. And instead of A here, I have there A Hermitian A. Okay? So if I define the matrix B is equal to A Hermitian A, what can you say about such a matrix? If I take its Hermitian, then Hermitian of this matrix would be the Hermitian of the one. The order will change, and I will take the Hermitian of each element. That is going to be A Hermitian times A. Okay? So B Hermitian is actually equal to B. So even though if A is not Hermitian, then B is going to be a Hermitian matrix. So this is going to be a Hermitian matrix. Okay? So this is max. X is not equal to 0. X Bx divided by XX. Okay? And I know the result of this maximization by that theorem. When I have any Hermitian matrix A here, the maximum of this ratio is nothing but the maximum eigenvalue of this Hermitian matrix. Okay? Here, this Hermitian, even though A is not Hermitian here, the matrix B here turns out to be Hermitian, and that theorem becomes applicable. Okay? That means that the maximum, this is A square, is going to be the maximum eigenvalue, lambda max, of the matrix B, which is the Hermitian matrix, always, even if A is not Hermitian. Okay? But this is nothing but A induced norm would be the square root of lambda max of, instead of the B matrix here, I can put A Hermitian A. Okay? And this is the result that we can derive by using this Hermitian matrix property. So we see here that this is the induced norm of the matrix A. In linear algebra, sometimes this the eigenvalues of the matrix A Hermitian A, they are sometimes called as the singular values of the matrix A. So this is called as any eigenvalue of the matrix A Hermitian A would be called a singular value of the matrix A. Okay? And this is nothing but the maximum square root of the maximum singular value of A. So induced norm of A is nothing but when I choose L2 norms here would be the square root of the maximum eigenvalue of the matrix A Hermitian A, or it is the square root of the singular value of the matrix, maximum singular value of the matrix A. Okay? So we see that we can derive an induced norm from symmetric matrix properties, because the matrix A Hermitian A is always a Hermitian matrix. So this completes this issue. As a final case of the Hermitian matrices, we are going to see the so-called positive definite or positive semi-definite matrices. Let us write definition. A Hermitian matrix A is said to be positive definite if and only if the inner product XAX is strictly larger than 0 for all non-zero x's. Okay? And a Hermitian matrix A is said to be positive semi-definite if and only if XAX inner product is larger than or equal to 0 for all x. So these are the definitions of positive definite and positive semi-definite matrices. So a positive definite matrix, for a positive definite matrix A, this inner product is always strictly larger than 0 for any non-zero x's. So we see that when I choose x exactly equal to 0, then this inner product would also be equal to 0. It's trivially equal to 0 when x is equal to 0. Therefore, here, I want the positiveness only for non-zero x's. I cannot have positive inner product for all x's, because when x is equal to 0, this is always equal to 0. Okay? And the positive semi-definiteness is the requirement of this inner product to be non-negative for all x's. Okay? Because here equality is allowed, I don't really have to exclude the 0 vector here. So now what does this mean? This means that X Hermitian AX, this is what this inner product is, should always be larger than 0 for all non-zero x's. Okay? This is positive definiteness. And X Hermitian AX is always larger than or equal to 0 for all x's, and this is positive semi-definiteness. Okay? So here let me talk about the meaning of positive definiteness. We are going to look at the eigenvalues, and we are going to actually see that for a positive definite matrix, eigenvalues are always positive. And for a positive semi-definite matrix, we are going to see that eigenvalues are always non-negative. So we would see that these inequalities would be satisfied for the eigenvalues actually. Okay? But before that, I want to talk about the geometric meaning of positive definiteness and positive semi-definiteness. So for this L2 inner product, if you have the inner product of x and y, you know from, for example, high school that this is norm of x times, or from the first year, calculus or linear algebra, this inner product is norm of x, norm of y times the cosine of the angle between x and y. Okay? So if these are two vectors, this is my x and this is my y, and here this angle theta is determined by the angle between these two vectors, and this L2 inner product would always be equal to this number. Okay? Now here I'm going to look at the application of this inequality onto this. So this is x. Instead of y, I have ax. Okay? So I have x, I have ax, and I have cosine theta here. Okay? And this angle theta is the angle between x and ax. Okay? So when I have, if I have a vector x in R2, and when I multiply this vector with x, that vector is transformed. Okay? So this becomes ax. It is a transformed vector in general, and it's different than x. Sometimes, for example, for the identity matrix, ax is always equal to x. But if a is not equal to identity matrix, then I know that ax is can be different than the x vector. And this is the angle between these two vectors. Okay? Now, what does being positive for this inner product means? If x and y are non-zero vectors, then these norms would always be larger than or equal. If x and y are non-zero vectors, then these norms would always be positive. Okay? If x and y are non-zero vectors, these norms would always be positive. And then what about this inner product being positive would mean? If these norms are positive, and if this inner product is positive, then I know that cosine theta is going to be positive. If the inner product is positive, then the cosine theta is positive. If the inner product is negative, then the cosine theta would be negative. By the way, we can define negative definiteness and negative semi-definiteness by putting a smaller than sign here, or smaller than or equal to sign. Okay? They are defined in a similar manner. So here, if the cosine theta is positive, then the inner product is positive when x and y are non-zero. And if cosine is negative, then the inner product is negative. Okay? So here we are told that for a positive definite matrix, x-ax inner product is always positive. What does that mean? That means that cosine of the angle between x and ax would be always positive. If cosine is positive when? Cosine theta is positive if and only if theta is between minus 90 degrees and plus 90 degrees. I am here counting the angles only between minus 180 to 180. Of course, if I add there some 360 degrees, there might be other ranges here. But here I am counting the angles only from minus 180 to 180. So that means that cosine is positive if and only if the absolute value of theta is strictly smaller than 90 degrees. Okay? So for a positive definite matrix, I know that this inner product is always positive. If the inner product is always positive, then that means that the cosine of the angle between these two vectors would be always positive. If the cosine of the angle between these two vectors are positive, then that means that angle between x and ax would always be smaller than 90 degrees in magnitude. Okay? So A is positive definite if and only if x and ax, the angle between x and ax, the angle between x and ax is always smaller than 90 degrees in magnitude. Okay? What about positive semi-definiteness? Positive semi-definiteness gives us the possibility that cosine can be equal to 0. Okay? So in that case, this angle can be also 90 degrees for a positive semi-definite matrix. Okay? So A is positive semi-definite. Then the angle between x and ax is always, what am I going to say? Smaller than or equal to. Smaller than, or here I have strictly smaller, equal to 90 degrees in magnitude. Okay? So when I look at a positive definite matrix, if I start with a vector x, then ax can never be like this for a positive definite matrix. This angle between x and ax can never be larger than 90 degrees. Maybe I should draw it like, so I'm really sorry. It's really stupid. So ax can never be in this direction. Okay? So this can't be ax, because if A is positive definite, this angle between x and its transformed version can never exceed, the angle can never exceed 90 degrees. Or ax cannot be like this either. It cannot, the angle cannot be strictly larger than 90 degrees in magnitude. Okay? So ax can be like this, or ax can be like this. These are possible, and similarly ax can be like this. The angle can be smaller than 90 degrees in magnitude, but it can never exceed 90 degrees in magnitude. Okay? So this is the geometric meaning of positive semi-definiteness. For positive semi-definiteness, 90 degrees, ax being orthogonal to x is allowed. For positive semi-definiteness, for positive definiteness, 90 degrees is not allowed. But for positive semi-definiteness, ax being orthogonal to x is allowed. This is the general meaning of positive definiteness and semi-definiteness. They are geometric meaning. Okay? It is always related to the angle between x and its transformed version with A. What is the angle between x and its transformed version? Of course, this is true for all x. I need to write here. Okay? The angle between x and ax is always 90 degrees in magnitude if x is not equal to 0, and this is true for all x. Okay? So now I have seen the geometric meaning of positive definiteness and positive semi-definiteness. The only thing remaining is to look at the property of an eigenvalue of a positive definite matrix. Let us write theorem. If A is positive definite, then all eigenvalues of A are positive. This is the first part of the theorem. If A is positive semi-definite, then all eigenvalues of A are non-negative. So what do we mean here? For the first part, we mean lambda I is strictly positive for all I, and for the other one, lambda I is larger than or equal to 0 for all I. So 0 eigenvalues are allowed for positive semi-definiteness, but 0 eigenvalues are not allowed for positive definiteness. Okay? So now we are going to just look at a very basic proof of this. So we know that xax is positive for all non-zero x's. Okay? This is the definition of positive definiteness. And here is what I'm going to do. Let lambda I be an eigenvalue of A with the eigenvector with the eigenvector EI. Okay? So let us say that we have an arbitrary eigenvalue of A, lambda I, and we have an eigenvector with the corresponding eigenvector EI. Okay? Can EI be equal to 0? Can the eigenvector be equal to 0? In this case, the answer should be no, because an eigenvector is by definition a non-zero vector. That means that EI is a non-zero vector, which means that it satisfies this condition. Instead of x, I can substitute the eigenvector EI, because EI is a non-zero vector. So in that case, this inner product, when I substitute x equals to EI, should still be positive. So EI is non-zero, therefore EI inner product with AEI should be strictly positive. Okay? And now I'm going to write what A times EI is. A times EI is lambda I times EI, because EI is an eigenvector. This is positive. And I can take this lambda I outside by taking its complex conjugate. But this A is a Hermitian matrix, so all of its eigenvalues are real. That means that conjugate of lambda I is equal to lambda I itself. So I can take it outside as it is. Lambda I, EI, EI. This should be positive. And this is lambda I times EI norm square. This should be positive. EI is a non-zero vector, therefore this norm is always positive. But since the multiplication is positive, the only possibility of lambda I, for the possibility lambda I, would be being positive. Okay? Because if lambda I is equal to 0, then this would not be positive. This multiplication would not be positive. And if lambda I is negative, the multiplication would be negative. Okay? So that means that lambda I should be strictly larger than 0. And since this was an arbitrary eigenvalue of A, then all eigenvalues of A should be strictly larger than 0. So here, an eigenvalue being larger than 0 does not make any sense when the eigenvalues are complex. So when you have a general matrix, then you cannot talk about its eigenvalues being positive or negative. Okay? Because the eigenvalues can be complex, and for a complex quantity, the positiveness or negativeness doesn't mean anything. So here we can talk about the positiveness of the eigenvalues because the matrix A is a Hermitian matrix, and all of its matrices, all of its eigenvalues are actually real quantities. So we can talk about their minimum and maximum, their positiveness or negativeness, etc. So here I can do the same proof for the positive semi-definiteness. Okay, it is really very easy. If xax is larger than or equal to 0 for all x, then I can substitute the eigenvalue and then eigenvector for x, and then I can show that lambda I is larger than or equal to 0. And this means that the eigenvalues are non-negative. Okay? They cannot be negative. They can be 0 or positive. All right? So this really completes the Hermitian matrix properties. And now we have only a final topic in this course, which is called the function of a matrix. And in the remaining 2 lectures, we are going to be seeing that topic. So in this course, as you see, my lectures are actually taking really long, unfortunately. I am exceeding the 50 minutes, and I thought about this, and I thought about the reason for this. So in general, in a real classroom, when I look at in the eyes of the students, I can see if they have understood a topic or not, or if they understood what I have written on the board or not. But here, since definitely I don't have any students here, the only thing that I see is a red light on that camera, and somehow it means to me that nothing is understood. So whenever I write something, I try to over-explain it again and again. And this is actually making the lectures quite long, and I'm not very happy about this, unfortunately. But I cannot compensate for this somehow. So I'm really sorry for the long lectures here, and I think it is caused just because of the fact that there are no students here, and I cannot get any direct feedback from the students when I try to explain something. So I'm assuming everything is unclear all the time, and I'm trying to over-explain it. So it's really something that I'm not happy about these lectures either. So sorry for this. But this is all for this lecture, and I would like to thank you again for watching. Bye-bye.